Remember, previously in the proof of Amitsur's theorem, we have used the following exact sequence. To describe the kernel of the restriction map from the Borel group of K to the Borel group of Kx, where X is a separate Borel variety, we have used exactness here. So this kernel is equal to the image of this map, and that's going to be equal to, by the first isomorphism theorem, Z mod out by the degree of the Picard group. And then we use the fact that if D is the period of X, i.e. the order of the class of X in the Borel group, then actually this Picard group is going to contain a divisor of degree D to see that this group is of size D. And why is that? Well, it's because by the geometric characterization of period, we know that we're going to have a Veronese D embedding on X. Here we are viewing X as a projective variety, subvariety of projective space. In other words, the linear system of degree D hypersurfaces on this Pn descend to a linear system on X, and that linear system induces a closed embedding into the projective space. Actually, the period D of X is defined to be the smallest positive integer such that this is true. Okay, so now the question is, how did we get this exact sequence? So how did we get that exact sequence? Well, it's gonna come from a relative exact sequence, then together with the snake lemma. So the relative exact sequence is as follows. Let's say L is a finite Galois extension of K that splits X. So X becomes isomorphic to the projective space over L, and let G be the Galois group of L over K. Then we have an exact sequence replacing the Borel group here with the relative Borel group. We will prove this relative exact sequence in a later video, but now let's show how we will use that to show the exact sequence, to deduce the exact sequence that we're interested in. So when we say that we have the exactness of this sequence, in particular what we will have is that the kernel of this A is equal to the image of this connecting homomorphism delta. Right? Now, when we want to deduce the exactness of this sequence, what we want to show, because this part is the same, what we want to show is that the kernel of this restriction map is going to be equal to the image of delta. So what we need to show is that the kernel of this map, this restriction map, is equal to the kernel of this map A. And for that, we use the snake lemma. So we have the following commutative diagram, right? And here these are exact. Here, this is the restriction map, and here's the map A that we have here. So by snake lemma, we have an exact sequence here. Thus, it suffices to show that the kernel, this last kernel, is 0. So this map is injective. If this map is injective, then this must be an isomorphism, right? And so the kernel of the restriction map is going to be the same as the kernel of this map A here, and so it's going to be equal to the image of delta, and thus the sequence is exact. So now we want to show that the restriction map is injective.